again. Time to start work on the rate of reaction content for A-level. The rate of reaction fits on the back of GCSE, but you know, you're in year 13. Maybe it's a while ago. What can you remember? First of all, it's probably not quite the way that rate was defined. Maybe not even have been defined at GCSE. It says that, and I realise my pen, I got the wrong pen now, it's a bit faint, but it says rate, how fast a reactant is consumed by a reaction. Now there are lots of ways to think about that, fairly similar. So you're looking at a reactant disappearing, and the point of when it says how fast is you look at it against time. Therefore you get a measurement versus time per second. That'll be the part of the units for it. Now GCSE wise, 5 variables. Can you think what they are? Hopefully you can. You've got them. I'm hoping you have. The classic. The most dramatic. Never looked at. The one everybody struggles to understand at the beginning. And the one there aren't many experiments to show at GCSE, but there we are. So concentration, temperature, pressure. Pressure behaves the same as temperature, behaves the same as concentration. So the effect for pressure is only related to gases. So I'm just going to ask you to pause me in a moment, and can you write the relationship between how fast a reaction goes, which I need you to call rate, and yeah, you should be making notes. You are. So the link, or the relationship as it should be called, between concentration and the rate of the reaction, and then for the other 4. I'm going to ask you to pause the video and do that, and then we'll just check that you've written the right sort of things down. So relationships. See you in a sec. So hopefully you wrote that if the concentration increases, you'll get a faster rate of reaction. So the higher the concentration, the faster the reaction. You can write it the other way. The lower the concentration, the slower the reaction. That's what happens in reactions as they take place, is the concentration of reagents, if they're in solution that is, goes down. Result, the whole thing starts to slow down. Temperature, increase the temperature, increase the rate of reaction. You can write it as the converse, with decrease slows down. Pressure, increase the pressure, faster rate of reaction if everything is reacting as a gas. Surface area, higher the surface area, faster the reaction. So that means, in GCSE terms, smaller lump size, as they probably called it, smaller particle size in terms of the solid material, up to powders being very fast indeed, which you may have seen. Catalyst, presence of a catalyst increases the rate of a reaction. You may also have written that it lowers the activation energy, or you may have written that it provides an alternative route through the reaction. Both of those are valid things to also have said. So those are the relationships, or something along those lines, I was hoping you would write. However, that's GCSE. At A level, it begins there. There's nothing wrong with that, and it develops into some particularly important A-level content in a number of facets. But the first one of those is very straightforward. How do you calculate the rate from a reaction? And it's a gradient thing. So I'll see you when I've got the board ready, and we'll go from there. See you in a moment. Okay, so before we can start talking about the data, you've got to know what sort of data you could have collected, which is why the heading there is what can you monitor. Because monitoring the rate of reaction is not just a case of just looking at it. You need some kind of physical change that you can, well, make a measurement numerically of, because it's all about graphs. So that's what you need there. You need something that you can make a measurement of. Concentration. Now, really, all of these are related to concentration. That's kind of the key factor in A-level rate, is it's all about concentration. And the thing about accessing concentration is it's quite difficult. If you're going to access concentration, how are you going to access the concentration of a particular chemical if you can't just look at the solution and it gives you a number? So what do? Well, if you're going to do concentration, you could do a titration. That is a possibility, and there are lots of experiments at A-level that you could do where rate and titrations come into it. But there's an issue with that, which I'll come to a little bit later. Something a little bit more familiar is mass lost. So you've got a gas escaping, so the mass of the reaction decreases. And it increases. That's wrong, isn't it? It doesn't, it decreases. It decreases the mass over time, but that speed with which it is decreasing starts to decline as time goes on, and it slows right down. Colour change. Now if you've got something that's coloured, it might fade or it might appear. How do you get a numerical measurement of that? There's a device called a colorimeter, often used in biology more than in chemistry. But it gives you a numerical reading for how intense the colour is of a particular thing that is coloured in solution. Yeah, a lot of things are in solution for this. Gas capture. Capture the release of a gas into, now at GCSE that may have been into a measuring cylinder. Not so good. Better off if you can trap it in a gas syringe. They only go up to 100, but it's better off if you can do that. You can do the level of a precipitate. And what this does is it obscures, usually you put a cross on a piece of paper and you time it until, I can't see the cross anymore. That's not as good as these things, because you only make one measurement with that. Please note that down. You only make one measurement with that, so it's a one-shot thing. These you measure every 30 seconds, so that's really helpful, because that means you can get a graph much better. This has its place when you're looking at temperature more than anything else. Conductivity. Now, conductivity might not be something you're familiar with. Conductivity is an expression of how easy it is to get electrical current through a solution. The more ions there are, the better it will do that, particularly hydrogen ions. They're very good at conducting. So if the level of ions changes from the reactants to the products, the conductivity will change. pH. pH is actually a concentration measurement, but it's easy to do because you have a pH probe put in and attach it to a digital meter. And every 30 seconds you can read the pH, and that was directly tracking by calculation. You can get the hydrogen ion concentration, you can get the OH concentration if you do the KW calculation as well, if that's what you need. So there is an issue with concentration. I'll come back, sorry, I've just not done these ones, but there are other things you can do. I particularly like the idea of dilatometry, which is where a solution, because of the number of particles in it, changes size. But it doesn't change size, obviously, so you do it in a very careful way. I like that. A thing called refractive index, physicists will like that. And chirality, which you may be familiar with, you can watch the grow or the decreasing, the amount of chirality in a solution. If you want to know more about these, you're going to have to look them up yourself, because they don't tend to appear very often in A-level questions. It tends to be these ones. Concentration. Why is it an issue? Because reactions don't stop when you want them to make a measurement. So these ones where you go, it's 30 seconds, what's the volume of gas that I've collected in a syringe, is very instant. Concentration itself, if you've got to do perhaps a titration, is not instant. So the reaction carries on when you want to know what the concentration is. It just carries on and changes concentration whilst you're waiting to make the measurement. So if you're going to do a titration, so there's a thing you have to know about called quenching, which is what I'm going to put on the board after I've cleaned it. I'll see you in just a second. So just a little bit about quenching. Quenching is literally taking the reaction. Now, the way you tend to do things where quenching is going to be involved is you have a big container of reaction and you take a portion of it out with a pipette, on a proper titration pipette. So the reaction is in a big vessel and you sample at time intervals the reaction and do a titration is where I would usually expect that to go. And what you're trying to do is the portion you take out, you stop it in its tracks. Now the best way is if you've got a reaction that has a couple of reactants, not the one that you're trying to measure, but one of the other ones, remove it completely. Now you can do that usually by putting in another chemical, and it just takes that chemical out of the system because it reacts it all away, and the one you're going to measure is left hanging and frozen. So you stopped that chemical at that moment. That's the best way, and there are a number of experiments you could do with that where you take a portion out, add something, one of the reactants goes, it all goes, and the whole thing is trapped, ready for titration at your leisure. If you can't do that, the next best way to quench something is drop the temperature right down. You drop a load of ice cubes in. Not as good as that because reactions still carry on at cold temperatures, they just carry on a lot slower. So that is like not true quenching because it doesn't stop it in its tracks, but it slows it right down and you get on with the titration really quickly. The worst one, and if it's the only option, it's the only option, is you take out your portion, you drop it into a whole load of water to dilute the concentrations down so much and get on with the titration really quickly. Much less accurate in terms of time than if you can just stop the reaction in its tracks. What we're going to go on to now is having got something that you have made measurements with over time, and we're going to look at a particularly straightforward reaction, initial rate of reaction and graphs. I'll see you when I'm ready. So we're going to do, well, we're not going to do the experiment, this is the thing. If you look up online you'll be able to see people carrying out this experiment. Very straightforward reaction, marble chips, calcium carbonate chips, limestone chips, and hydrochloric acid. You put the two together, it fizzes carbon dioxide, loses mass. You record the mass of the entire experiment every 30 seconds, or depends on what you're doing, you might do longer intervals near the end because it's not changing so much. And you record the mass of the experiment at those time intervals. And what have you got? Well, you've got a set of data. I have a set of data that is in the text that accompanies this video. You see more information about the video and it's there as a document to download. Before you can do the rest of this video, you need that graph plotted. It's a graph that will go up and flatten off. If you haven't got any A4 graph paper, there is also a downloadable sheet of A4 graph paper, which you'll need two of when you print them out, because you're going to need to hand plot the graph, really, because that's what you're going to do under exam conditions. And best fit curve. There's no anomalous data in there, it should be a pretty good curve. But you need to complete the data in the table, because you don't plot the mass of the experiment. What you plot is how much mass it has lost at that point since the beginning. So it's a cumulative mass loss. So as time goes on, the mass loss gets bigger and bigger, but the way it changes, it slows right down and hardly changes at all near the end. So the total mass loss becomes fairly constant at the end. You're going to need to plot that graph. Like I said, it's going to come out as a data that rises up like that and flattens off. That's it really, until you've plotted the graph. And there is going to be a second set of data that we'll talk about in a moment. And then when you come back, we'll move on. See you in a second. So you should have a graph that rises up and flattens off. if you've let the video run and you haven't plotted the graph, you need to stop me now, rewind a little bit, plot the graph, because that's what we should be doing, is analysing the graph that you've plotted. Now, what we're looking at is calculating the initial rate. Now, the initial rate is obviously from the early parts of the reaction. Now, the reality is when you do this experiment, there's a little bit of a lag at the beginning where carbon dioxide saturates its solution in water, and then the reaction releases carbon dioxide into the air and you get the mass loss. But I've ignored that and just gone, let's just go with a set of data that makes it easy to process. But I have seen that question, is why is there a little flat bit at the beginning and it's carbon dioxide dissolving in water before it can be released. This is my ruler. This is not a ruler, but it's the easiest thing to use. What you need to plot is a tangent line. Now, on most of these, the tangent line, if you don't know what a tangent line is, it's a line that touches the curve at the point of time, in this case, because time is our independent variable here and dependent variable up there, at the point in time that you need to measure the rate. So if we were looking to measure the rate here, you would need your tangent line to do that. It's a line that touches the curve at the point where you wanted it to be. I put a dot where I wanted it to be. So you do that by putting the pencil, you need a sharp pencil, at the point where you want to plot it, and you bring the ruler up to it so that it doesn't cover any of the curve of the line. However, I want initial rate. So initial rate is much easier because it's at the point where the reaction takes off at the beginning. Now, most of the time, these things here are pretty much straight up the curve. And they track the curve. The curve hasn't even had a chance to start to flatten. And then you need to do a gradient triangle. In terms of calculation errors, I've got a Chinook helicopter flying over my house at the moment. In terms of getting a decent value for it, the bigger the line and the bigger the triangle, the less error there will be in your calculated gradient. So having that line longer and doing a bigger triangle will be much better. And standard gradient thing is the two changes. For the mathematicians, oh dear, that's not gone very well. Dear, mathematicians among you, it's a differential thing of dy over dx, but in reality, we're chemists, we don't get involved in all of that business. So we just do how big is y, how big is x, and you get a value for the gradient. I'm going to ask you to stop the video, get your line from point 0 to get on there, get your tangent line at point 0, find its gradient, and when you come back after doing it, I'll tell you what you should have got. I'll see you in a moment. Okay, so, and I will have put my Excel graph up that I use to generate this so you can see, hopefully yours looks similar. The gradient should have been round about 0.025. Yeah, you've got to do it with the units that are on there. So you've got to do the change in mass, in however much of a gram it was, and the change in time. But it has to be in grams per second. So if you did your gradient and you got a value of about 0.025, then you've done reasonably well. You don't have to get it exactly 0.025, it's a real thing. Now there is a second set of data, and I want you to plot the second set of data. You'll need a new piece of graph paper. I'll see you after you've plotted the second graph. So when you plot the second one, kind of longer axis on the time, goes up to 12 minutes. Should have got a gradient of 0.013, but it's less likely that you'll get the two gradients exactly what I have than you would like. Reason? You're plotting it over the entire time of the reaction and you get the flattening curve that you often see. That's why I want you to plot a third graph. Just the first 60 seconds. Because when we're talking about initial rate, we don't care about what happens 5 minutes into the reaction. We're just looking at the first few seconds, really. Because it's quite an important thing to analyse about rates of reaction. So I want you to plot a third graph. I may have said you only needed 2 pieces of graph paper earlier. You need 3. I am sorry, but it's there to click and download. So just the first 60 seconds, and then do the gradients again. I probably won't need a tangent line because they'll just be plumb straight in the first 60 seconds. Okay? Plot that graph and I'll see you with your gradients off that graph after you've done it. See you in a moment. Okay, so when you do that, you'll get something along the lines of that where there are 2 distinctly, obviously different gradient lines. And you've got a gradient, you should get nearer to the values that I said, the 0.25 and 0.013. You should be nearer to those 2 values this time because it's easier to get the gradient because they're not so steep. So it's because you were getting a short difference in time, and now you're getting a full size difference in time on the graph. So my question is, what was the difference in concentration for the 2 sets of data? And if you look at the concentration, gradient, you look at the gradient, one is half the other. So this one has half the gradient of this one. So this one, you began the experiment with half the concentration than you did this one. This one was twice the concentration of this one, but both the same statement, but which way around you want to word it. Why is this important? Because one of the types of analysis you do of rate of reaction under exam conditions is called initial rate questions or initial rate comparison questions or comparative rate questions. They all mean the same thing. Where you get a set of data where it's looking at initial rates. But you can't do that kind of question yet, because before you can do that, you need to understand about a really important thing called the rate equation. The rate equation? That's a whole video in itself, and that'll be what I do next. I will see you in that video. I will see you very soon for the rate equation and all the things that means. Thank you for watching, and I'll see you soon. Bye bye.